The transformations used in computer graphics are used for geometrical transformations. In the case of projections, the perspective projection is the most common. Other approaches are the axonometric projection and combinations of different projections and views. A more recent method is a 3D object morphing transformation in terms of control elements of modeling means. In terms of simulation, it is either morphing an object in a time continuum, for example, an aging, a disintegration, etc., or morphing an object after an interaction, a collision. In general, both defining and modeling, as well as subsequent transformations or object projections, are among the basic processes applied in computer graphics. In these cases, the curves and surfaces are often used also for graphical object definition or modeling. But the curves and surfaces are used in the computer graphics area, in particular, for two reasons. The first one, mentioned above, is their usage in the area of graphical object modeling. The second reason, nowadays, with a rising trend, is to use them in the background as the control attributes of various activities used in the computer graphics. Each curve or surface must have its mathematical description for a possibility to perform various transformations with a curve/surface, such as shifts, rotations, or scale changes. They are also used for 3D scanning post-processing. Here you can use these curves/surfaces designed in different shapes but with one big plus. This represents the knowledge of the mathematical notation, equations, of a curve or surface. Thus, it is possible, for example, to easily calculate the length of curve and surface area or simply shape it. Overall, it is not necessary to work with all curve/surface points but only with some curve/surface control points. The non-uniform rational B-spline, NURBS, curves/surfaces are the most flexible and also most applicable. Some curves and surfaces are usable also in some cases of special type of displaying. It is also possible to use 3D displays instead of 2D ones. The examples of 3D displays are volumetric and holographic displays. Then a visualization and visibility solution are no longer needed. These types of displays are still relatively low robust and low performance devices at a very high cost. However, this does not mean that their usage is irrelevant in the future. The performance of current computing systems allows the real-time displaying of spatial objects. The results from this area are already widely used in architecture, engineering, and film, movie, industry. Displaying spatial objects began to develop with the development of the first graphical display units. Initially, it was the display of simple wireframe models. Next, the surface of the body itself was displayed, but it was only a matter of filling the object surface with one color or simple shading. In addition, the algorithms have been developed to allow photorealistic imaging of spatial objects, allowing the display of shadows and reflections on object surfaces. But even so, it was only a piece of information about a three-dimensional space that did not allow or in part to gain spatial information from a given output. The solution, though it seems to be only partial, is to explore and exploit the very way in which human receives visual information and thus an examination and an exploitation of spatial vision. Stereoscopic imaging is between 2D and 3D displaying but bringing to a viewer a sense of depth or space. Stereoscopic vision is one of the basic characteristics and abilities of people, as well as many other forms of life on Earth. The stereoscopic projection is based on the principle of displaying different images into each eye through a special device such as glasses with different colored glasses, anaglyph, switchable glasses, polarizing glasses, stereoscopes, or helmets/glasses for virtual reality, also with mobile devices usage. For example, a color space image can be seen by an observer through switchable glasses. On the displaying device, the image for the left and the right eye is alternately displayed, and the right and the left eye are obscured in sync for the observer. The color space image can be seen also by the observer through the polarizing glasses. Both the left and right eye images are simultaneously displayed on the displaying device, but they are polarized in perpendicular planes. Overall, the perceived depth of the image is an important part of modern type displaying, for example, in virtual reality systems. The development of new technologies within computer systems and within modern computer graphics too is taking on a dizzying pace. One of the areas where progress is most noticeable on a daily basis is undeniably virtual reality, next VR, and its related technologies. VR uses computer graphics in a wide range. A virtual reality system is an interactive computer system that is capable of creating an illusion of physical presence in an imaginary or near real world, synthesized by the VR system. A VR system provides a perfect simulation in a tightly bound human-computer interaction environment. Thanks to the technological advances and decreasing prices, various VR devices are becoming more common in research, industry and entertainment. These are, in terms of mass interest, resulting of financial returns, a long-term draft horse of technological advances in associated technologies including computer graphics. Despite the indisputable advantages that the modern solutions of the VR provide, it is not a common practice to use them within a professional environment. Primary, systems based on classic user inputs and outputs such as a keyboard, a mouse, and a conventional 2D monitor continue to dominate. Although interfaces are an important feature of VR systems, they are not only the one and at all not main. The ability to create an illusion of physical presence in synthesized space, or to influence the real space with synthetic elements, can be considered dominant. The first imagination of the perfect VR was presented in the cult movie The Matrix and its continuations. What is real and what is virtual? VR systems provide a better experience, and they are more interactive, but the complexity of their implementation is very high. VR subsystems are divided according to senses that affect visualization subsystem, acoustic subsystem, kinetic and statokinetic subsystem, touch and contact subsystem, and other senses, for example, smell, taste, pheromone sensitivity, etc. Some senses commonly perceived in the real world do not have much importance to implement in the virtual world at present. However, the visualization subsystem is the most important, and so computer graphics is at the first place in this case. Visual immersion is very important. The virtual cave in the Lierke's laboratory at the Technical University in Košice and the examples of immersive visualizations within this cave are shown in Virtual Cave in Laboratory Lierke's at Technical University of Košice and the examples of immersive visualization in this environment. The above-mentioned areas of computer graphics are just some of the wide range of current computer graphics. The overview of modern approaches, procedures, algorithms, as well as devices in the area of definition of graphical scenes and objects, light and colors, graphical transformations and graphical libraries and systems, projections, curves and surfaces used in computer graphics, visibility solving, filling and texturing, shading and lighting, realistic and photorealistic imaging, stereoscopy and spatial imaging, image filtering or user interfaces, and virtual reality should be the content of this course.